Hello students, hope you have enjoyed my video lectures on Coulomb's law and superposition principle of electric forces. After this lecture, you will be able to solve problems on electric forces. So we start with our problem 1. It states that a free football A of 8 grams carries a positive charge of 5 into 10 to the power minus 8 coulomb. What must be the nature and magnitude of charge that should be given to a second football B fixed 5 centimeters below the former ball so that the upper ball is stationary? So I have already noted down the data already given. We have considered mass of football A as M1 is equal to 8 grams, that is equal to 8 into 10 to the power minus 3 kg. Charge of football A, that is 5 into 10 to the power minus 8 coulomb, and you can see the separation between these two footballs R is equal to 5 centimeters, which is equal to 5 into 10 to the power minus 2 meter. We also know that 1 by 4 pi epsilon 0 is equal to 9 into 10 to the power 9 Newton meter per coulomb square. Small g, acceleration due to gravity, 9.8 meter per second square, and I need to find out the nature and magnitude of charge Q2. So first thing we can see is that the weight of this football A, M1G, is acting in the downward direction. So in order to keep this football stationary, this Q2 charge must be positive so that it repels A, and it will provide a repelling force in such a fashion that F1 is equal to M1G. They become equal in magnitude and opposite in direction. So we can easily write F1 is equal to M1G. We know that F1 means 1 by 4 pi epsilon 0. We are considering free space, so I am writing 1 by 4 pi epsilon 0. Q1, Q2 by R square, that is equal to M1 into G. So you can substitute the values. 1 by 4 pi epsilon 0, that is 9 into 10 to the power 9. Q1 given 5 into 10 to the power minus 8 coulomb. Then you have Q2, I need to calculate this, divided by R square, that is 5 into 10 to the power minus 2 meter. So 5 into 10 to the power minus 2 whole square, that is equal to M1, that is 8 into 10 to the power minus 3, and G, acceleration due to gravity, that is 9.8 meter per second square. So I can easily write an expression for Q2 from this. So I have Q2 is equal to 8 into 10 to the power minus 3 into 9.8 into 5 into 10 to the power minus 2 whole square, whole divided by, I have 9 into 10 to the power 9, 5 into 10 to the power minus 8. So I can see that Q2 is equal to 8 into 10 to the power minus 3 into 9.8 into 5 into 10 to the power minus 2 whole square divided by 9 into 10 to the power 9 into 5 into 10 to the power minus 8. So if you solve this, value comes out as 4.36 into 10 to the power minus 7 coulomb. And I already mentioned that Q2 must be positive because it needs to repel Q1 so that it can counterbalance weight of pithball A. So this must be positive. Okay, so this is how you can solve. We are now switching to problem number 2. So we consider statement of problem 2. 2 point charges plus 4Q and Q are fixed at a distance A apart. Where should a third point charge capital Q be placed between them on the line joining the two charges so that it may be in equilibrium? So you can see that I have considered that the positive charge Q is at a distance x from plus 4Q charge. So it means plus Q charge is A minus x distance apart from small q. To solve the problem, we assume that Q is positive. I consider Q is positive. Then the force experienced by plus Q charge due to plus 4Q charge will be in the outward direction, that means toward right. I am considering this force to be F1. Okay. Similarly, the force experienced by capital Q charge due to small q charge will also be repulsive. As a result, the force will be acting to the left. Let it be F2. So for equilibrium, I can easily say F1 is equal to F2. If we consider free space, then I can write it as 1 by 4 pi epsilon 0 plus 4q into q divided by x square, that is equal to 1 by 4 pi epsilon 0 plus q into plus capital Q into plus small q divided by a minus x whole square. So this is a minus x whole square. Now you can see from the figure, I have deliberately drawn plus q to the right. It is not exactly at the middle. Reason is, if I have this magnitude to be greater than this magnitude, it means that numerator of this expression is large. So denominator must also be large in order to make this ratio equal to this ratio. And that's why I have drawn the position of plus q deliberately to the right, not exactly at the middle point between plus 4q and plus q. If you now simplify this, you can easily see that 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0 cancel each other. X square will be there, a minus x whole square, that will be there, 4 will be there. So I can easily see this is 4 into a minus x whole square, that is equal to x square. Okay, so I can easily write it as, you can easily write it as 2a minus x, that is equal to plus minus x. So I can have two solutions. One is 2 into a minus x is equal to plus x. So that gives you 2a minus 2x is equal to x. So if I simplify this, I can see x is equal to 2a by 3. Or if I consider this negative sign, you have 2 into a minus x, that is equal to minus x. So 2a minus 2x is equal to minus x. So x is equal to twice a. But I have already mentioned that plus q charge must be between plus 4q and plus q. So I can neglect this result. I have this value of x which indicates a distance from plus 4q and in between plus 4q and plus q. So result will be x is equal to 2a by 3. So that's the answer. But again I have second part of this problem. The second part states that in which case the equilibrium will be stable and in which case unstable. So again we start with this q is positive. So let q be positive. Then what happens? If you shift this plus q slightly to the right, you are shifting this plus q slightly to the right. So what happens? This separation will decrease and this separation will increase. As a result, F2, repulsive force experienced by capital Q, will be repulsive force F2 experienced by capital Q due to this small q will be stronger than this F1. So I can easily write that F2 will be greater than F1 if Q is shifted to the right. So there will be some unbalanced force or resultant force, and the value of this is F2 minus F1. But if you check the direction of this F2 minus F1, of course it will be acting toward the larger force F2. So resultant F2 minus F1 will be acting in this direction. That means this resultant will push capital Q toward its equilibrium position. Same happens if we initially shift capital Q to the left. In that case F1 will be greater than F2. So resultant force will be F1 minus F2. Resultant force will be acting toward F1. So that resultant force will again push this plus Q to the right. That means toward its equilibrium position. So it means that this is the case of stable equilibrium. Both forces actually push this plus Q to remain in its original position or equilibrium position. So this is the case of stable equilibrium. But if we now consider that Q is negative, now I consider that Q is negative. So what happens? So let Q be negative. So now this Q will actually attract plus Q. So this F2 will now act in this direction. Whereas this capital Q is also attracted by this plus 4Q charge, so F1 will be in this direction. Now, if you shift this capital Q slightly to the right, as a result, F2 will increase and F1 will decrease. So now what happens? Again, you have some resultant force which is F2 minus F1. So as before, you can see that F2 is greater than F1 and there will be some resultant force F2 minus F1. But now this resultant force is acting to the right. It means it will pull plus Q to the right further. So that means this plus Q will never return to its original position, that means equilibrium position. Similarly, if you start with the condition that Q is shifted to the left initially, in that case F1 will increase, F2 will decrease. So resultant force will now be F1 minus F2. That resultant force will be acting toward plus 4Q. So again, this resultant force will attract it toward plus 4Q. That means this Q will never return to its previous position. That means equilibrium position. That is why when you take Q as negative, it indicates unstable equilibrium. I hope you have understood the concept of stable and unstable equilibrium. Now we consider problem number 3. So the problem statement is two pith balls weighing 10 to the power minus 3 kg are suspended from the same point by means of silk threads 0.5 meter long. On charging the balls equally, they are found to repel each other to a distance of 0.2 meter. Calculate the charge on each ball. So I consider that the charge on each of these balls to be small q. Okay. Now you can see when you have situation like this, each ball is suspended in air and they maintain some equilibrium condition like this. So I need to consider the forces acting on each of these balls. So I don't need to consider two balls actually. I may consider force acting on only one ball. You can easily solve the problem even then. So I am considering that. You can see the mass of this pith ball A is M. So weight is mt, that is acting in the downward direction. These two pith balls repel each other. So the force experienced by this pith ball A due to ball B will be in this direction. This is force of repulsion. Along with this, there is a third force which is also known as tension that will be acting along the length of this thread, because ultimately this silk thread holds this ball at this position. So there must be a third force which is tension acting toward the point of suspension. I may take components of this T in the horizontal direction and in the vertical direction. If I consider this angle to be theta, this angle is also theta. So you may easily understand that this component of tension will be T cos theta. That is very simple. You can understand that base by hypotenuse equal to cos theta. So base is equal to hypotenuse into cos theta. That is why you are getting T cos theta. Similarly, if we consider this component, this must be T sin theta. So again you can see perpendicular by hypotenuse is equal to sin theta. So perpendicular must be equal to hypotenuse into sin theta. This is equal to this, so I am writing T sin theta over here. Now for equilibrium, I need to consider the forces acting in the horizontal direction and forces acting in the vertical direction separately. In the horizontal direction, you have F is equal to T sin theta. Similarly, in the vertical direction, mg must be equal to T cos theta for equilibrium. So net force acting in the horizontal direction must be equal to 0 and net force acting in the vertical direction must be equal to 0. Okay, so that is what I have considered, just equating the magnitudes only in the horizontal and vertical direction. So if I divide equation 1 by 2, I get F by mg is equal to tan theta. Now I need to calculate this tan theta. If you look into triangle OAC, which is a right angle triangle, you have hypotenuse OA is equal to 0.5 meters. You have normal AC that is equal to 0.1 meter. So you can easily calculate this base OC, that is equal to root over 0.5 square minus 0.1 square meter. You just apply Pythagoras theorem, which is perpendicular square plus base square is equal to hypotenuse square. So from this formula I can calculate OC. So tan theta is equal to AC by OC, that is equal to 0.1 divided by 0.5 square minus 0.1 square. So from this you can easily write F is equal to mg into tan theta, and you have F is equal to 1 by 4 pi epsilon 0. If I consider these two charges to be equal to Q, so it is Q square by R square, that is equal to mg into tan theta. So you can easily say 1 by 4 pi epsilon 0 is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. Q square you need to calculate, divided by R square. R is equal to 0.2 meters, so 0.2 whole square, that is equal to mg M is equal to 10 to the power minus 3 kg, G 9.8 meter per second square, tan theta I have already calculated tan theta. This is actually 0.1 divided by square root of 0.5 square minus 0.1 square. So I got 9 into 10 to the power 9 into q square divided by 0.2 square is equal to 10 to the power minus 3 into 9.8 into 0.1 divided by square root of 0.5 square minus 0.1 square. So if you solve this equation, you will get Q is equal to 9.4 into 10 to the power minus 8 coulomb. So this is the answer. I believe that you have understood. So we will now consider problem number 4. The statement of problem 4 is charges of plus 5 microcoulomb, plus 10 microcoulomb and minus 10 microcoulomb are placed in air at the corners A, B and C of an equilateral triangle ABC having each side equal to 5 centimeters. Determine the resultant force on the charge at A. So you need to solve this problem. You can easily understand that this is an equilateral triangle, so all angles are equal to 60 degrees. If we consider force on A due to B, which is a repulsive force, will be acting in the outward direction. Let this force be F1. If we consider force on A due to C, this is a force of attraction. So it will be acting in this direction. Let this force be F2. If I want to calculate the resultant force at point A, or resultant force experienced by plus 5 microcoulomb located at A, I need to consider law of parallelogram of addition of forces F1 and F2. So if we now add these two forces, I get this resultant force, say this is F. Now if we consider this parallelogram, the angle between these two forces will be 120 degrees. Okay, so if I calculate the values for F1 and F2, then I apply law of parallelogram to find out the magnitude and direction of the resultant force. I am done. Okay. So I am trying to solve this. If I consider F1 must be equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. We already know 1 by 4 pi epsilon 0 is equal to 9 into 10 to the power 9 Newton meter square per coulomb square. Q1, say I am considering this as 5 microcoulomb. So this is 5 into 10 to the power minus 6 coulomb. Then I am considering this Q2. This is Q2, say. Then this will be 10 microcoulomb. So that is 10 into 10 to the power minus 6 coulomb divided by R, 5 centimeters. I have to convert this into meter. So I have 0.05 meter and whole square of this. So if I now calculate this, I will get the value to be equal to 180 Newton. It acts along dA. If I now calculate F2, I will be getting same magnitude, because you can see charges are same, distance is also same, only direction will change. So if I substitute all these values as before, you have 9 into 10 to the power 9 like this, Q1 as before, 5 into 10 to the power minus 6, Q2, so I am considering its magnitude, so this is 10 into 10 to the power minus 6 divided by distance between them 0.05 meter square. So you calculate this, you will be getting 180 Newton along, now it will be acting along AC. If I now apply formula for magnitude of resultant force in terms of F1 and F2, I can write F is equal to square root of F1 square plus F2 square plus 2F1 F2 cos angle between them. This angle is 120 degree. So if you now substitute the values, F1 180 square, F2 square, that means again 180 whole square, then you have 2 into 180 into 180 cos 120 degree. So if you solve this again, its magnitude will be 180 Newton. Now I have to find out its direction. I am considering that the resultant vector is making an angle beta with F2. Then I can calculate tan beta. Tan beta is equal to, I have considered angle between resultant and F2, so that should be F1 sin 120 degree divided by F2 plus F1 cos 120 degree. So F1 sin 120 degree divided by F2 plus F1 cos 120 degree. So F1 as before 180 sin 120 degree, you can easily calculate. The value is sin 120 degree is equal to cos 30 degree, okay, which is nothing but root 3 by 2. Then you have 180 plus 180 into cosine 120 degree. You can also calculate cosine 120 degree. Cosine 120 degree comes out as minus sine 30 degree. So that is minus half. So if you substitute all these values, you will be getting the result to be equal to 1.732. That is actually root 3. So you can easily say that beta is equal to 60 degree. Tan beta is equal to root 3. That means tan 60 degree. Okay, so this is how you can solve problems on superposition principle of electric forces. I have solved one problem using 3 charges placed at 3 corners of a triangle. You may have problems with 4 charges placed at 4 corners of a quadrilateral or a square or rectangle, whatever. Okay, you can easily solve this problem, that problem also. Okay, so I hope that you have understood how to solve problems on electric forces. Thank you.